Hi everyone. This is a demonstration of the experiment called the determination of manganese content in steel. The first thing that we need to do is to make a set of 4 solutions of potassium permanganate. So this is the concentration of the potassium permanganate solution that we're going to use.
Hold on, go on a little bit. There we go. All right.
And I have already poured that solution into beaker number 1. You can see that there's about 60 milliliters in there. You can see that the potassium permanganate solution is a nice pink color. The experiment calls for making 3 more solutions using that potassium permanganate solution. And so I'm going to show making solution number 2, which in the instructions calls for 30 milliliters of the potassium permanganate and then 10 milliliters of deionized water. So I'm going to go ahead and make that solution, make solution number 2. Again, that was 30 milliliters of potassium permanganate solution. So I'm going to pull that solution up into the pipette, and then of course we need to drop that meniscus down to the mark, and then I transfer that to the beaker number 2, and I'll do that 3 times since this is a 10 milliliter pipette. Again, you remember that in pipetting we always touch the tip of the the pipette to the inside wall of the flask so that the surface tension of the liquid can help draw out what needs to draw out. So that was 10 milliliters, and we'll do another 10 mil. So there's 20. And again, by way of reminder, as we're draining the pipette into the beaker, when it gets down to the end, we do not shake the pipette, we don't blow it out. There's a little bit of the solution that remains in the tip, and that is intended to remain there. Okay, so that was 20 milliliters, and now one more 10 milliliter aliquot here. Aliquot is just a fancy word for a known portion of a sample. And so again, because I'm taller, that's why I hold this up so that I can see the meniscus straight on rather than breaking my back by trying to bend over and do it. Okay, I have added 30 milliliters of potassium permanganate to beaker number 2. I'm going to set that pipette aside so I can use that one later. I'm going to get a fresh pipette to use for water. And again, the procedure calls for adding 10 milliliters of water to beaker number 2. So of course, by adding the water, that will change the concentration of the solution in beaker number 2. Okay, so we'll add 10 milliliters of water to the solution that's already in beaker number 2. And then we will make the solutions in beaker number 3 and in beaker number 4. I'm going to go ahead and pause the tape at this point and make those solutions. I don't have to show you how to make those. Okay, so just to reiterate, This beaker number 1 contains the potassium permanganate solution, and then in beaker number 2 we put 30 milliliters of the contents of 1 into number 2, and we added 10 milliliters of water to that. In beaker number 3, I took 10 milliliters of the contents of 1 and put it into 3 and added 10 milliliters of water to that. And beaker number 4, I took 10 milliliters of number 1, put it into number 4, and added 30 milliliters of water to beaker number 4. And you can see that they have slightly different shades of pink depending on how much they have been diluted. Okay, this is a spectrophotometer, specifically what we call a Spectronic 20. And this is an instrument that can measure the amount of light that passes through a colored sample, and it will measure then how much light is being absorbed by that sample. This instrument has several dials on it that we need to learn how to use. The dial on top of the machine is the wavelength, and for this experiment we're going to be working at a wavelength of 525 nanometers. So I'm going to turn the wavelength dial until the wavelength is reading 525 nanometers. That would be the wavelength of light that is going to be shining through the sample when we measure it. Also on this machine, I might add, there's a lever down in the lower left part of the instrument that depends on which wavelength that we're using. On the left, it says from about 340 to 599 nanometers, which is the range that we are working in today, so I've got the lever over there. On the other hand, there might be other times that I'm working in a range between over 600 nanometers. It says 600 to 950, and so if that were the case, I'd move the lever over to the right. But today, since we're at 525 nanometers, I'll leave the lever over on the left. Now we have to zero out the instrument. We have to, in a sense, tell the instrument what it looks like when there's nothing in the light path, and what it looks like when there's just pure water in the light path, that is allowing all of the light to shine through. So this is where the sample will be placed, and for this operation we're going to use a test tube that just has deionized water in it, and that will go down into this slot here. But for now I'm going to use the knob on the left to set 0% transmittance. There is no sample tube in the sample holder, and so I'm just going to turn this knob until the reading on the display says 0. It won't matter if it says negative or positive 0 because those are the same thing. Okay? And what this means is that there is no light shining through a sample. There's no sample even, and so 0 light is being transmitted. Now we're going to show the machine what it looks like when we have pure water in there. And again, I've got that in the test tube. This instrument is sensitive to fingerprints on the glassware. It will read oils on your fingerprints as if there's something to be absorbed, and so I wipe that off. Then I put the test tube into the sample holder, push it down all the way in. And now I'm going to use the knob on the right, which says 100% T, and I'm going to change that to make it read 100. And again, what this means is that 100% of the light is being transmitted through that pure water. And we can tell that that would be the case because pure water, of course, has no color, meaning that none of the light that is shining through it is being absorbed. Okay? And so we set that now at 100, and sometimes this is just a little bit touchy, and it takes just a little bit of effort to get it to read that, and now it wants to read 100.2. And that will be adequate on this machine. If it says 99.8 or 100 or 100.2, that will be fine. Okay, so now we are ready to measure the absorbance, not the transmittance, but the absorbance of the 4 solutions that we've made. I'm going to take the solution that was in beaker number 1, and just pour some of that into test tube labeled number 1. And we want it to be about 1/2 to 2/3 full. The light the light in this instrument will shine through about the bottom third or so of the test tube. And so if I have the test tube about 1/2 to 2/3 full, that is adequate. Again, I'm going to wipe the fingerprints off. I'm going to take the blank out of the sample holder and put test tube number 1 in its place. And this time, rather than reading the transmittance, I'm going to use this mode button to switch over to the absorbance. And we want to read the absorbance of that solution. And so you can record that absorbance in your notebook. Okay, now we're going to take that one out and do the same thing for the rest of the samples. So beaker number 2, pour that into test tube number 2. And wipe off the fingerprints. And then measure that absorbance. Now you can record that absorbance in your notebook for beaker number 2. Do the same thing for number 3. And there's the absorbance reading for beaker number 3. And finally, solution number 4. Make sure to wipe off the fingerprints. And put solution 4 in its place. We'll record that absorbance as well. As you can see, the absorbance has decreased with each one, and that's because we have less and less potassium permanganate in those solutions, which means there's less and less light being absorbed by the permanganate. Okay, I have weighed out a sample of steel. You can see this is what it looked like in the tube. It's been ground up previously. This is sample A72, and I have weighed sample out, and you can see the mass over there, 0.115 grams of steel has been weighed out. I'm going to pour it into a small beaker. And I tap the weigh belt to make sure that all of the steel gets into the beaker, and then I'm going to add to it, I need to add to it 10 milliliters of the 1 to 3 nitric acid. Okay, so this is 1 to 3 nitric acid. I'm going to get 10 milliliters in here. And the exact quantity of this is not critical. I'm just going to go ahead and empty out the pipette. It is a little bit more, but since what I'm interested in is the steel sample, I've carefully measured that, and all of these other ingredients are now in excess, just to make sure that the reaction goes as necessary. Okay, so I'm going to add the nitric acid to the steel sample, and you perhaps notice that I am working in the fume hood, because this will, as it dissolves, will create brown fumes. This reaction needs to be heated, so I've got it on the hot plate, which has already been warming up, and in a little bit you will perhaps see some brown fumes coming off of the steel. I'm going to put a watch glass on here and start to warm that up. The purpose of the watch glass, of course, is to minimize the vapor loss coming from the sample so that we don't lose too much water vapor from there. But this takes just a little bit. You may recall in a different experiment where we used nitric acid to dissolve copper, and that went very quickly, and you saw the brown fumes. Now you're starting to see the steel starting to bubble, and you may see now starting to see the vapor inside being trapped by the watch glass, that it's beginning to turn yellowish brown in there. That is the nitrogen dioxide gas, NO2 gas, that is being produced as a result of the reaction between the steel and the nitric acid. The reason we're doing this in the fume hood is because the nitrogen dioxide gas is a toxic gas. If you were to breathe that into your lungs, it would react with the moisture in your lungs and turn back into nitric acid, which would not be a very pleasant experience. So you can see there's quite a bit of brown fumes being given off there, and occasionally what I will do is just open up the lid, so to speak, and let that escape. Of course, this is going into the fume hood. Where does that go? That goes through a filter before it is released into the atmosphere outside. So we just have to let this heat for a while. The procedure suggests that we heat it until the steel dissolves and the brown fumes disappear. So we're going to pause the camera and just let it do its thing for now. Okay, so the steel sample has, for the most part, dissolved. I'm not going to ask the camera to zoom in on this, but there is a very small amount of black material that does not seem to be dissolving very well. One of the components of steel is often carbon, and this sample of steel apparently has a little more carbon in it. Carbon does not react with nitric acid, and so what we do to dissolve the carbon is to add ammonium persulfate. So in the procedure, it calls for about 0.2 grams of ammonium persulfate, and you can see that it's a white crystalline substance, and that's about 0.2 grams there. I'm going to go ahead and add the ammonium persulfate to the steel sample, and so I'm just going to shake that in there, and then just go ahead and add that again. Okay. So this ammonium persulfate is going to react with the carbon. Even if there wasn't any visible carbon, we'd still want to add it so that we can make sure that all of the carbon has been converted into carbon dioxide. The procedure now calls for us to boil gently for 10 minutes and perhaps add water if we run a little bit low on water. So I'm going to turn the temperature down just a little bit, and we'll let that go for 10 minutes. Okay, we've had the solution boiling. It's been reacting, as you recall, with the ammonium persulfate, and that has been for about 10 minutes. So I'm going to take the watch glass off, and then I'm going to take this off the hot plate. And the procedure calls for adding 20 milliliters of deionized water first. So we'll add that. And it says to do this in order that we add 2 milliliters of concentrated phosphoric acid. So here's the phosphoric acid. I'm going to use this dropper pipette. Up to about here is 1 milliliter. So get about 1 milliliter in there, put that in, and do another one. Now the purpose of the phosphoric acid is to bind with the iron. Iron itself in solution is slightly yellow, and we want to not have any of that showing up on the spectrophotometer, and so we add the phosphoric acid to it, and then we add about 0.1 grams of potassium periodate, KiO4, and so I've already measured that, and we'll add the potassium periodate to the solution. And the purpose of the potassium periodate then is to cause the manganese, which is currently in the Mn+2 state, and oxidize that to convert it into the MnO4 ion, the permanganate ion, MnO4, which is the pink solution, or the pink color that we saw earlier with the standards. So we're converting the manganese, Mn2+, into MnO4- with the potassium periodate. Now we let this stand on the hot plate for 3 minutes, and at some point we will see it start to turn pink. So we are going to keep the camera rolling on this part of it. It's kind of an interesting change. We never know from one sample to the next which one might turn pink rather quickly, or which one just takes its merry old time, and then finally, when you've almost given up hope, that it suddenly turns pink. So we'll just keep the camera rolling on this one. Not seeing any pink yet, but we often see it developing nearest the pile of potassium periodate that you may be able to see in the middle. And maybe it's my imagination, but I think I'm beginning to see some pink developing around that KiO4. And now I know it's not my imagination. It is starting to turn color. Go ahead and take this off a moment. I can swirl this a little bit for stirring purposes. And the suggested time frame in the procedure of 3 minutes is really just a suggestion. What we really, of course, want to do is make sure that all of the KiO4 has dissolved and that it has turned as pink as it's going to get. If I were to just do a strict time of 3 minutes and take it off at 3 minutes, we may not have had the entire reaction occur. So we just want to make sure that it's all reacted. Now you may begin to see some pink tint occurring in the solution. Of course, I guess the other part of this is it's not technically boiling yet, so we may have to let it go a little bit longer. Now definitely turning pink, but the KiO4 is still undissolved in the bottom of the beaker, so again we want to be sure that that has all dissolved and has all reacted with the manganese that was in the steel sample that we started with. still is some KO4 in the bottom of the beaker. So we'll see if we can actually get this to be boiling a little bit. Looks like it's gotten a little bit darker even as I've been waiting here. So I think we'll go ahead and pause the camera right now, and we'll get it to boiling, make sure that it's boiling well. Okay, so we've got it boiling, and it's been boiling for a little bit, and so we can carefully take off the watch glass. And then take this off of the hot plate, and we need to let it cool for a little bit and then transfer it into a volumetric flask. So we'll go ahead and let that cool. Mostly we don't have to cool it down to room temperature yet, but just so that we can handle it easily without burning our fingers while we're transferring it into the volumetric flask. Okay, it has cooled enough now for me to be able to handle this without burning my fingers. You see that it is a nice purple color, so we're going to put it into the 100 milliliter volumetric flask. And the procedure calls for a quantitative transfer. And so what I'm going to do is first pour all of this in here, and then I'll use my wash bottle to rinse the beaker out a couple of times into the volumetric flask as well, and that will make sure that I get all of the permanganate ion out of the beaker and into the volumetric flask. The reason for transferring it into a volumetric flask is so that I can dilute it to a known volume, so that we know so that we will be able to calculate what the concentration of the permanganate is. So one more rinse of the beaker into the flask. Then I'm going to add water to it. Now at this point I don't want to bring it up to the mark just yet, because the solution is still somewhat warm, and I need to have my solution at room temperature in order to bring it up to the mark. So I'm going to take this to the sink and allow cool water to run over the outside of the flask in order to cool the contents. If I were to bring this up to the mark while it was still warm, I would have a false volume, because as the solution cools, the volume would decrease, and so I would not have actually 100 milliliters in there after it had come back to room temperature. Okay, this has cooled off now. Try this a little bit. So now I'm going to finish adding water. The mark is about where my finger is pointing. I'm not going to use the wash bottle to bring it all the way up to the mark, but I'll bring it up, maybe half a centimeter or so below the mark. That's about a centimeter, but that would be fine. And then I'm going to finish off by using a dropper to add the last little bit of water, because after all of this work that I've done, I don't want to overshoot the mark. So I'm just going to add the water gradually to it until the bottom of the meniscus is on the line. There it is. And now, as always with volumetric flasks, we have to make sure that it is well mixed. And so the recommendation is to turn this upside down and shake it maybe 15 to 20 times. And that ensures that the last little bit of water that I added at the top gets well mixed throughout the entire solution. Okay, so at this point we are ready to measure the absorbance of this solution. So we'll go back to our spectrophotometer, and the spectrophotometer has been on the entire time. We don't have to remeasure it, but I am going to double check the 0 point to be sure that it has not drifted. So I'm going to use the mode button to go back to transmittance. Again, when there's nothing in the sample holder, that should be reading 0 transmittance. And I'm going to put the blank, I've wiped off the fingerprints, I'm going to put the blank back in there. And on percent transmittance, we need to set the blank to read 100. So it's drifted just a small amount, but not much. Just going to reset that to 100. 100.2. Okay, we mentioned that earlier. And now I'm going to simply pour some of my solution into a test tube. Use the Kim wipe again to wipe off the fingerprints. Put that in there. Adjust the mode button to read absorbance. And you can record that absorbance in your notebook for this sample. And we're going to do that twice more. So get another test tube, get another sample. So this is the second aliquot, and you can record that absorbance. And then we'll get the third reading on it. Now that's the third reading, and so now that is the end of this experiment.